Today's topic is three-phase transformer connection or vector group of transformer. Actually, we will have some vector group. What are those groups? We will see in part 3 here. And we will have to perform connection for these vector group. What is meant by connection here? So let us see a practical transformer. This is a three-phase transformer. Here we are able to see three windings. This winding will have two terminals, one upper terminal and one lower terminal. This winding will also have one upper, one lower, and here also one upper and one lower terminal. So there are total 6 terminals, but there are 3 more windings. One inside this winding, one inside this, and one winding inside this winding. And this internal winding will also have one upper terminal and one lower terminal. So we will get 2 upper terminal and 2 lower terminal. You can see here there are 2 upper terminal and we will get 2 lower terminal, 2 upper, 2 lower, 2 upper terminal, 2 lower. In this manner, we will get total 12 terminal. Let us draw these windings on board so that I can show you these 12 terminal very clearly. So these are winding of three-phase transformer. One primary and one secondary for R phase. One primary and one secondary for Y phase, one primary and one secondary for phase B. Here we get total 12 terminals. I have marked this terminal as A1, A2, B1, B2, C1, C2, and secondary winding by a small letter A1, A2, B1, B2, C1, C2. I have represented primary winding here. This is schematic diagram. I have represented all primary winding at one side and all secondary winding at other side. This winding is A1, A2, A1, A2. Here I have shown. Now suppose primary winding is to be connected in star. So I can connect this terminal and this terminal to one point, A1, B1, C1 to one point. So primary winding has been connected in star. Now we will connect A2 to line A, B2 to line Y, and C2 to line B. This connection is in star. The schematic representation of this connection I am going to show here. This is the same connection as here. This winding is A2, A1, A2, A1, this winding A2, A1. A1, B1, C1 gets connected with each other. This winding is B2, B1, and this is C2, C1. A1, B1, C1 gets connected to each other. Now, if I want to connect these windings, so I can connect these windings from this diagram and from this diagram also. A1, B1, C1 gets connected to one point. So we will connect A1, B1 and C1 to one point, and from A2 line R is to be taken from terminal A2, line R. From B2, line Y is to be taken, line Y, and line B from C2, line B from C2. So here I can represent this line as line R because it is to be taken, R is to be connected from A2. Line R is to be taken from A2. From B2 line Y, and from C2 line B. From B2 line Y. From C2 line B. Primary winding has been connected. Now secondary may be in star or delta, but these star or delta can be performed in different ways. So we have to learn these different ways we will see this in part 4. Actually, I have divided this lecture into 5 videos. It is so because if some student knows basic points already, then, or if anybody is not interested in basic points and he want to learn connection only, then he can get to this part directly. But I am giving the basic points for those students who want to know the reason that why we need to study this topic. So in part 1, I will tell you that how or why line voltage leads phase voltage Vp in star connection. In part 2, we will see overview of parallel operation. In part 3, we will see 3 points. 1. Which type of connection can be used for parallel operation? Second point, meaning of Y0, Y6, YD1, DY1, etc. And third point, in same part, that different vector group we will see in this part. And in part 4, we will learn how to connect, how to perform the connection in part 4. In part 5, we will see remaining connection. Let us see how or why line voltage leads phase voltage in star connection. See here, when supply is given, then a flux is set up. So V1 is induced in primary winding and V2 is induced in secondary winding. If flux changes, V1 also changes, but V2 changes simultaneously. Suppose flux changes such that V1 is increasing, at the same instant V2 will also increase because the same flux links both the windings. It means, suppose if it is time itself, at any instant V1 increases, then at the same instant V2 will also increase. Suppose at this instant V1 attains its maximum value, at the same instant V2 will also attain its maximum value. And the instant at which V1 becomes 0, V2 will also become 0 at the same instant. It means V1 and V2 are in phase. Whether windings are connected in star or delta, but the voltage in these windings are in same phase. Here also the voltage induced will be in same phase. Here also the voltage induced will be in same phase. But suppose we want to measure voltage between A2 and B2. Means we want to measure voltage this R line and Y line. Means if I want to measure voltage VRY, then VRY will not be in phase of V1 and V2. VRY will lead this voltage by 30 degrees. So we will see that how line voltage leads phase voltage. Actually, all of us knows a phasor diagram. This phasor diagram, this is PR, VY and VB. From this phasor diagram, we can find VRY. Actually, we know VRY equal to VR minus VY or VR plus minus VY. So, to get VRY, we will add VR and minus VY. We will add these two. We know VY is this. So, where is minus VY? We will get minus VY here. It will be minus Vy, opposite to plus Vy. Now from here we will add Vr minus Vy. So we will get Vry as this. This is Vry. From this figure it is clear that line voltage Vry leads phase voltage by 30 degree. But this figure is representation only. From this figure we can get that Vry is leading Vr by 30 degree. But from this figure we are unable to get the exact reason, the actual reason that why line voltage leads phase voltage by 30 degree. And one more point, that here we have taken Vry equal to Vr minus Vy. If we had taken Vr plus Vy, then Vry would have been this much. But it is not so. Why? Why we are taking Vr minus Vy? So let us see actual connection of winding. How windings are connected? In this manner. This is R phase, Y phase and V phase. This winding cause current to flow in this direction, and here direction of current is like this, and here this. So now we can represent this winding by voltage source as, actually this winding tries to flow to cause current to flow in this direction. So we will show this winding by this voltage source, and it is R phase, so it is VR. What is this? B phase. Y phase is this one. It is VB, and this is VY. This is R line, this is Y line. Now, if we apply KVL between these two terminals, then what is VAB? VAB is nothing but VRY, and VRY equal to VRY after applying KVL. VRY, VAB equal to VRY equal to VR minus VY, because these two voltage sources are opposite to each other. So VRY equal to VR minus VY. Now one can have a doubt that if VRY equal to VR minus VY, then how VRY is greater than VR? So let us see the actual diagram of voltages, that is waveforms of voltage. So this is the actual diagram of three voltages, that is VR, VY and VB. Previous figure was phasor diagram, that is representation of VR, VY and VB. But actual diagram is this one. Here we have to find VRY, and we know VRY equal to VR minus VY. So here no need of VB, because we are interested in VR and VY. So no need of VB. So I am erasing VB so that figure becomes simple. Now, VR minus VY or VR plus minus of VY. So, we will add VR and minus VY. We know VY, that is plus VY. We do not know minus VY, but from this we know that minus VY will be opposite to plus VY. So, from this waveform we can get VY minus VY. So what will be minus VY? Minus VY will be this one. This one is minus VY. Now no need of plus VY, so I am erasing this one plus VY. Now VR equal to VR plus minus VY, it means we have to add VR and minus VY. This is minus VY minus VY. Now we will add these two waveforms. Here what is VR? 0, and it is here it is minus VY this much. So VRY will be equal to minus VY at this instant. Here it is VRY. Now at this instant VRY will be somewhere here. At this instant VRY will be somewhere here. At this instant VRY will be maximum, and at this instant VRY will be at some lower point, somewhere here. So in this manner we get waveform of VRY, and it is like this one, like this. So now I am raising Vy. From this waveform, it is clear that VR is greater than VRY is greater than VR. VRY is greater than VR. Now we have to see phase difference between VRY and VR. That's why I have raised V minus Vy. Now see, VRY attains maximum value at this instant, and VR attains its maximum value at this instant, and this is pi by 2. So from this waveform it is clear that VRY and VR has a phase difference of 30 degree. Now actually you have to remember this point, that line voltage leads phase voltage in star connection, and as I have already told you that phase voltage of primary is in phase with phase voltage of secondary. I have told you. So you have remember that point also and this point also, because it will help you to understand that why we need different type of connection. Now in part second we will see overview of parallel operation. Thank you.